And now let's discuss the third topic in pharmacokinetics, which is metabolism or biotransformation. As we said before, for our drug to be excreted outside our body, it's excreted through urine, but we would have difficulty in the excretion of the drug in urine because most of our drugs are more lipophilic than being hydrophilic. So our drugs are not water soluble enough. So our lipophilic drug must be first metabolized in the liver to a hydrophilic metabolite easily excreted in urine. Our drug is converted to a hydrophilic metabolite through adding a polar water-soluble molecule to it. But there is a problem. The drug being lipophilic would have difficulty in being added to a water-soluble molecule. They wouldn't mix together. It's like mixing fat with water. So there must be a linkage between this lipophilic drug and the water-soluble molecule. This linkage is polar functional group. It acts like a handle. This polar group could be OH, COOH, NH2, or SH. And to this polar group, the water-soluble molecule would be easily added, and then our drug would be converted into a hydrophilic metabolite. And so we can say that the metabolism occurs on two steps or two phases. Phase number one, which is called functionalization also, in which a functional polar group is either added to our drug through a certain reaction or it is unmasked. So for example, COOH here could be a part of an ester in the molecule. So we can unmask it through deesterification. So this was our phase one. Phase number two is called conjugation, in which we link or conjugate the polar group of phase one to the water-soluble molecule. Alright? Okay, for phase one reactions, these reactions include oxidation, reduction, or hydrolysis. But what are the molecules that our drug is conjugated to in phase number two? Number one molecule is glucuronic acid, and this is the major one and the most common one. There is also sulfuric acid, acetic acid, and amino acids. What is the result of this metabolism, of these two phases together? We would mostly get a metabolite that is inactive. By the way, there are some molecules that can go directly into phase 2 reactions without passing through phase 1, because these drugs already have handled, they have already these polar groups. Alright? Now let's back again to the point of the result of the metabolism. We would mostly get a metabolite that is inactive. It no more could exert any reaction or any action in our body. But there are some exceptions to this, and the metabolite could be more active. Let's take an example. The analgesic drug morphine. This drug is conjugated with glucuronic acid in phase 2 reactions. Two metabolites could be resulted from this conjugation reaction according to the position of the conjugation on the molecule. We could have M3G or morphine 3-glucuronide, which is inactive, and we can get morphine 6-glucuronide, which is even more potent than morphine. So, metabolism not always result in inactive metabolites. And the question here, what if our drug already have polar groups in its structures? As we learned that this drug would go directly into phase 2 reaction without passing through phase 1 reaction. Alright? Okay. Do you remember when we mentioned in our first lecture that our drug's name have a history or have a story behind it? Our drug morphine is one of these drugs. Morphine is a drug that treats pain. It is of plant origin. It is extracted from a plant called Papaver somniferum, and the pharmacist who discovered this drug named it after the Greek god of dreams, Morpheus, because he found that the drug morphine has a tendency to cause sleep, so he named it after the Greek god of dreams, Morpheus, morphine. Alright? Now we have discussed the phases of metabolism and the end result of it. So now let's see what the reactions of phase 1 and 2 is done by. Well, it's done by enzymes. And there are two large types of enzymes in the liver. It is either enzyme that is called microsomal enzymes and non-microsomal enzymes. Well, what are these microsomes that we named these enzymes after? What are the microsomes? Microsomes are vesicles that are not found as it is inside the cells, but these vesicles are reformed from pieces of endoplasmic reticulum. They are formed when our cells are broken up in the laboratory, and this microsome could be separated by centrifugation. So these microsomal enzymes are actually enzymes that are found on the endoplasmic reticulum of the hepatic cells. Okay then, what are these enzymes? The most important one are actually a group of enzymes that is called Cytochrome P450 or CYP450. And this family of enzymes is the group responsible for the oxidation reaction. And these reactions were one of phase 1 reaction. By the way, let's see from where these enzymes, Cytochrome P450, got their name. They are called cyto because they are bound to membranes within the cell. Cyto means cell. And chrome because they have heme in their structure. Okay? And this heme absorbs light at a wavelength of 450 nanometers. So this where the number in the name came from. And the P comes from the word pigment. Okay? Let's back again to our microsomal enzymes. Another microsomal enzyme is Glucuronyl Transferase. And what does this enzyme do? Yes, it is the enzyme responsible for the conjugation with glucuronic acid in phase 2. The rest of enzymes, either it is in phase 1 or phase 2, are non-microsomal enzymes. So the microsomal enzymes are the cytochrome P450 group or family of enzymes, which is the family responsible for oxidation, which is a phase 1 reaction, and glucuronyl transferase enzyme, which is the enzyme responsible for conjugation with glucuronic acid in phase 2. Alright? Before we move on to the next point in metabolism, we have to discuss the nomenclature of cytochrome P enzymes. Each individual enzyme in this family has a different name. How are they named? For example, we would found an enzyme called Cytochrome P3A4 or CYP3A4. So after the word CYP, we found a number, and then there is a letter, and there is a number again. The first number indicates the family this enzyme is from, and the letter indicates the subfamily, and then the second number is for this individual specific enzyme. Okay? Now, we finished the introduction of metabolism, and we will now discuss a very important property of the hepatic microsomal enzymes, the microsomal enzymes in the liver. Let's discuss. Our hepatic microsomal enzymes or liver microsomal enzymes, they have a property that they are inducible. And what does that mean? That means that the rate of synthesis of these enzymes can be increased by an inducer. And of course, increasing the synthesis of these enzymes would result in higher activity. Also, there would be inhibitors of these enzymes. So, the inducers are expected to increase the synthesis and hence the activity of the enzymes. And if the activity of the enzymes that breaks down the drug is increased, this would of course decrease the plasma concentration of this drug. And on the other side, the inhibitor would reduce the synthesis and activity of the drug, of the enzyme, and this would decrease the breakdown of the drugs metabolized by this enzyme, increasing its concentration in plasma. These inducers and inhibitors of the enzymes could be drugs. So we can find a drug that is inducer for an enzyme that metabolize another drug, and another drug that is inhibitor to this same enzyme. So now let's take examples of drugs that are inducers and drugs that are inhibitors. For the inducers, we have the drug phenobarbital. This drug is a hypnotic drug, a drug that induces sleep. This drug is a derivative of an acid called barbituric acid. Okay, what about telling the story behind this name, the name of barbituric acid? The part barb in the beginning of the name has many stories. One of these stories was that the chemist who synthesized barbituric acid named the compound after Saint Barbara because he discovered it on the feast day of Saint Barbara. And the part uric in the name comes from urea because barbituric acid is synthesized from the reaction of urea with an acid called malonic acid. And this we can see in the structure of barbituric acid here. This upper part in the structure is urea, and this lower part we have a dicarboxylic acid in which between the two carboxylic here there is one carbon, and this dicarboxylic acid with one carbon between the two carboxylic is called malonic acid. Alright, we have also another inducer drug which is rifampicin. Rifampicin, or also called rifampicin. This is a drug that is used to treat tuberculosis. This is anti-tuberculosis drug. For the inhibitors, we have ketoconazole, which is an antifungal drug, and we have omeprazole, which is a proton pump inhibitor used to treat peptic ulcer. The significance and importance of the inducers and inhibitors drugs is when any of them is taken with another drug. If an inducer drug is taken with drug X, it would be expected that its concentration in the plasma would decrease. So we would expect less activity of this drug. And on the other side, if an inhibitor drug is taken with drug X, it would be expected that the metabolism of drug X would decrease. So that means that its concentration in plasma would increase. So we would expect more activity of this drug in the body. So inducers and inhibitors drugs, when taken with other drugs at the same time, this can cause drug-drug interactions. Now let's see examples for these interactions. If we took a protease inhibitor, a drug that is used to treat human immunodeficiency viruses or HIV, with rifampicin, which is used to treat TB, and which we said that it is hepatic microsomal enzymes inducer. So we would expect that rifampicin would increase the metabolism of the protease inhibitor. So this would result in a decrease. This would result in a decrease in the concentration of the drug, and hence the HIV replication would increase, and we would observe a failure in therapy. Okay, let's take another example. What if someone took omeprazole, the drug that is used for treating peptic ulcers, with warfarin, a drug used to prevent the formation of blood clots? Omeprazole is an hepatic microsomal enzyme inhibitor drug, as we mentioned before. So we will expect that omeprazole would decrease the metabolism of warfarin. So this would result in increase in the concentration of warfarin in plasma. And this drug is an anticoagulant drug. So if its concentration is increased in plasma, we would observe bleeding. Alright? Okay. Speaking of the stories behind the names of the drug again, let's talk about the name of warfarin. Warf in the name of warfarin stands for Wisconsin Alumni Research Foundation. Wisconsin Alumni Research Foundation. Wisconsin Alumni Research Foundation, this is the organization that has supported the research that discovered this drug. And the part "arine" in the name comes from coumarin, and it is the chemical compound of warfarin. Alright? Okay. Now let's discuss the last topic in metabolism, which is the kinetics of metabolism. Let's discuss it. Suppose that we gave a dose of 100 milligrams intravenous of a drug. Then, after 6 hours, we found that the amount of drug in plasma became 50 milligrams. So, these 6 hours here, we can call it the half-life or the T-half. Okay, because our drug decreased to half of its initial amount. Okay, now let's suppose that we doubled the dose given to 200 milligrams instead of 100 milligrams. Then we measured the amount of the drug in plasma after the same 6 hours. And then we found that the amount is 100 milligrams. So the drug also reduced to half its initial amount. So again, this 6 hours here is also the half-life or the T-half. Okay, so we gave double the dose of 200 milligrams. We gave 400 milligrams of the drug, and we measured the amount of it in plasma after the same 6 hours, and we found it to be 200 milligrams. So again, this 6 hours is the T-half. Alright? Let's take a look at another drug. We gave 100 milligrams of this drug, and then we measured the amount in plasma after 6 hours, and we found the amount to be 50 milligrams. So this 6 hour would be our T-half here. No problem with that. Then as we have done with another drug, we also increased or doubled the dose to 200 milligrams. And then we measured the amount in plasma after 6 hours. We found it to be 150 milligrams. So only 50 milligrams were metabolized, and the rest is found in plasma, which is the 150 milligrams. So, can we call that 6 hours here the T-half? Of course no. Then after another 6 hours again, another 50 milligrams of the drug were metabolized. So we ended up with 100 milligrams of our drug in the plasma. So our drug, to reach its half of its initial amount, it needed more time. It needed 12 hours, not 6 hours. And these 12 hours here is now our T-half. So our T-half became longer when we doubled the dose of our drug. Okay, what about giving 400 milligrams of this drug as we had done with another drug? After 6 hours, the same 50 milligrams only were metabolized, and we ended up with 350 milligrams of the drug in plasma. So, to reach 200 milligrams, which is half the initial amount of 400, we would need much longer time. Okay, let's say that the drug on the left is drug X and the drug on the right is drug Y. Which of those drugs, the metabolism or the elimination, is directly proportional to concentration? Meaning that when the concentration increases, the elimination rate also increases, and vice versa. Yes, this is drug X. When the concentration was doubled, the elimination was also doubled at the same time. When the amount was 100 milligrams, we eliminated 50% of them in 6 hours. And when it was doubled to 200 milligrams, we also eliminated 50% of them in 6 hours. While for drug Y, the elimination rate is constant. We have constant elimination rate. Whatever the concentration is, we always eliminate 50 milligrams every 6 hours, even if we increase the concentration. Okay? Now, for what drug the T-half is variable? Yes, drug Y. While for drug X, T-half is constant. We eliminate half of the drug every 6 hours, whatever the concentration is in drug X. Okay? Now, another question. In which drug we eliminate constant amount? Yes, drug Y. Because 50 milligrams of the drug is eliminated every 6 hours, whatever the concentration is, while we eliminate constant fraction or percentage in drug X, because we eliminate 50% of the dose every 6 hours, whatever the concentration is, while in drug Y we eliminate 50 milligram every 6 hours. We eliminate a certain or constant amount. Okay, the kinetics of drug X we call first order kinetics or linear kinetics, because when we increase the concentration of the drug, the rate of elimination is increased also, and the kinetics of drug Y is called zero order kinetics. Alright, we also call it nonlinear kinetics. The enzymes of metabolism of first order kinetics, we can call them strong enzymes, while the enzymes of zero order kinetics are weak enzymes. Why we call the enzymes of first order kinetics or that follow first order kinetics are strong enzymes? Because they increase their power according to the concentration. So you increase the concentration as you want, and they would do their job. On the other side, the enzymes of zero order kinetics is somehow weak. They have limited capacity. They are saturable enzymes. They only can metabolize a constant amount. And thanks to God, most of our drugs follow first order kinetics. See, so we wouldn't expect a real toxicity from them, because by increasing the concentration given, the rate of elimination also increases. But some drugs follow zero order kinetics, so we should take care when dealing with them. Examples of drugs following zero order kinetics are aspirin, phenytoin, and ethanol. Phenytoin is an anti-epileptic drug, a drug that is used in the treatment of epilepsy. And now we finished our third point in pharmacokinetics, which is metabolism. We would discuss now our last point, which is excretion.